Testing. Yep, we've got audio. All right. So good evening, everyone. We have more than full house tonight in the Space Science Lab here, and we'll talk about why in a moment. But if, again, anyone that isn't sitting that would prefer to have a seat in the physics lab, that is an option for you. The live stream that's going on right now is on the projection screen in there. So that's an option, and what's also nice about live streaming is that you can tune into this presentation again after the fact. So if there's something you want to hear again, maybe a new question comes to mind you want to ask in our comments, things like that, those are options on the recording afterwards. So that's on the Kopernik Observatory YouTube channel. And we have a little camera right up near the projector that is going to track the show up front. So hello to our live stream viewers. My name is Jenny Carty. I am one of the science educators here at Kopernik Observatory and Science Center. And this summer has been super busy. We've had so many different programs happening. This past week we had a summer camp up in here, Space and Stars. We're running summer camps throughout the season. Next week we have super science discoveries and virtual universe. So different themes every week. And yeah, there's so much to explore up here at Kopernik. We're also doing a lot of on-the-road programs. We'll be at some libraries this weekend with the planetarium. So lots to do. We're out there, we're here, we're all over the place. So, and on that note, we do have a scout troop up here tonight that's passing through on their way up to Canada. So they're here, they'll be staying overnight this evening, and that's in part why we have such a jam-packed room here. So we're so happy to have them this evening, and they also brought along our presenter. So I think without further ado, we'll just head right into the presentation. This is Dr. Roberts from the Johns Hopkins Applied Physics Laboratory, and he's here today to talk about Europa Clipper. So we'll pass it over to Dr. Roberts.
All right. Is my mic on? We getting out? All right. Thank you, everyone. My name is Dr. James Roberts. I'm at the Johns Hopkins Applied Physics Laboratory. I am a planetary scientist, and I serve as the investigation scientist for gravity and radio science on the Europa Clipper mission to Jupiter's moon Europa. As you can tell by my attire, I am also an assistant scoutmaster for Troop 601 out of Columbia, Maryland, and an unbearable bear from the Course for the Wood Badge N6 22018-2. Since the dawn of time, humanity has been obsessed with understanding what lies beneath these ice shells. When our universe was first forged in the crucible of the Big Bang, concept studies for exploration of these ocean worlds were already well underway. In 1610, the four so-called Galilean satellites of Jupiter, the four largest moons, were discovered conveniently by somebody named Galileo with the new telescope that had been in use for some time, but Galileo was the first to think to train these on the heavens. And when he looked at Jupiter, which was just a point in the sky, it resolved into a disk, and there were four stars around it, which we now know as the moons Io, Europa, Ganymede, and Callisto. These are four of the largest moons in the solar system. Three of them are larger than our own moon, and Europa, the smallest of them, is nearly the same size as our moon. In the 1990s, we sent a spacecraft named after Galileo to investigate these. It stayed in orbit around Jupiter for 8 years. However, it wasn't able to send back nearly as much data as we'd hoped because the antenna didn't deploy. The high-gain antenna. We had to turn the spacecraft around and trickle home, basically using dial-up, what few bits we could get with the low-gain antenna. So what you'll see here is the family of Galilean moons. Moving outward from Jupiter, we have Io, which is the most volcanic body in the solar system. It is so volcanic that it basically resurfaces its entire surface every 50 years. Its largest volcano, Loki Patera, puts out more heat than the entire Earth put together. Moving out next, Europa is actually a rocky world, shrouded in a thin film of water and ice. Although we say thin, it's actually twice as much water as is in all the Earth's oceans combined. Moving out from there is Ganymede. Ganymede is about half water and half rock. It also has a liquid iron core. It is the only moon known to generate its own magnetic field. And finally, we have Callisto, which is so far out from Jupiter, it was never really heated, and it's just a mixture of rock and ice. So focusing on Europa, these are some of the images that we did manage to get back from Galileo. We can see these ridged plains all over the place, crisscrossing. And it looks like rifts on top of rifts, like the planet is splitting open. We have these terrains called chaos, where there seem to be blocks that are broken up and shoved aside and twisted in some ways. Sort of like little icebergs that are frozen in place. There are very few craters, impact craters. Now, these are the best way we have of telling how old a planetary surface is. The older a surface is, the more craters will pile up on here. So this is it is one of the very few craters that we have. And so that implies that this is a very young surface. We also have these dark spots on here called lenticulae, which is a Latin word meaning dark spot. Everything sounds more profound if you say it in Latin. So we don't really know what these are, but they could be regions where something in the subsurface has poked its way up and is spilling this red material onto the surface. If we had a giant saw and could cut Europa in half, that would be awesome. And we don't have that, but this is what we would see. There's a thin, icy crust. We don't know exactly how thick it is, but something around 20 or 30 kilometers, 15 to 20 miles for those of you that prefer that system. Underneath that is a very thick water ocean, liquid water ocean. That is 100 kilometers deep. This is far deeper than even the Mariana Trench is on Earth. And that ocean is directly in contact with a rocky surface, just like the sea floor on the Earth. And inside of that is a metallic core. So we know all this from measurements we've made of the magnetic field and the gravity field from the Galileo mission. And I will answer questions at the end, but thank you. Please hold that. So here's a picture showing how much water there is on three very popular objects. We've got the Earth, we've got Mars, and we've got Europa. And everyone is going on about water on Mars. You read the news, every other month it seems they discover water on Mars for the first time. And yes, there was certainly water on Mars. There's even, you can see that North Polar ice cap. There's water on Mars today. And there was probably liquid water there in the past. But there's not very much of it, especially compared to Europa, which has way more than Earth's oceans. And so this is possibly the best place to look for life outside of the Earth. Now, it's so far away from the sun, how could it possibly be warm enough to support a liquid water ocean? Well, what we're seeing here is the process of tidal heating. If I can replay this graphic, Europa's orbit around Jupiter is not a perfect circle. It's an ellipse, which means that at times it is closer to Jupiter and at times it is farther away. When it's close to Jupiter, it gets stretched out, not nearly as much as is shown here, but by 30 meters or so. And if you look at what happens to the inside when you do that, the inside gets stretched and squeezed, and this dissipates a lot of heat in the interior. And so that keeps the water melted. So what we have here is the ocean, And then above that, a layer of warm, flowing ice. It's weird to talk about ice as warm, but we're talking the coldest temperatures on Earth. You get 100 below zero in Siberia or Antarctica. Out here, you're getting to about 100 degrees Kelvin, which is something like 400 below zero, 300. I don't work in Fahrenheit that much, but it's a lot colder. When you get to those temperatures, ice behaves like rock. So at the surface, you've got very cold, stiff ice. It's not going anywhere. But underneath, you've got warm, flowing ice like the glaciers on Earth. And so the warm material can move up and deliver its heat to the surface. And possibly you can make melt lenses like this, which could cause the surface to collapse in on itself. And so that might be one way you can form these chaos regions, is by melting it from underneath. And then, of course, once it's exposed to the surface, it freezes again immediately. So this is an artist's conception. We haven't actually photographed it to this quality of how the Connemara chaos on Europa might have formed. And that's Jupiter in the background. If you're anywhere on Europa, you look up in the sky, you see this wonkin' great Jupiter here. You might think it's nice to look up and see the moon. This is like several times the size of the moon. You will not forget that it's there. So Europa has all the ingredients for life. It's got water. It's got more than all of Earth's oceans. It's got, nutrients and minerals that are delivered by impacts. And you've got chemical energy coming in from above and possibly from below if you have like seamounts, volcanoes on the bottom of the ocean. We have those on Earth. That's how you form the Hawaiian Islands. So you can get chemical energy from that. And it's been just sitting like this for 4 billion years. So you've had lots of time for life to evolve. Now, it's probably not going to be, whales or squid. Or anyone seen the Europa report? Yeah, you don't need to see the Europa report. It's not going to be like that, but there might be bacteria or something like that. So here's a little video from NOAA on hydrothermal vents on the Earth. So this is life at one of these seafloor vents on the Earth with this volcanic material spilling in from the bottom, and it's providing heat and new chemicals. And so you see all this life. You've got worms here, and I think there were crabs, and all this is way below the surface of the Earth. No sunlight gets down here. So this is just like on Europa, where there's a thick layer of ice blocking it. So all this can happen without the sun. Okay. So based on that, we have devised a mission called the Europa Clipper. This is a dream-given form. 2,500,000 grams of metal, all going to be spinning around alone in the night. You've got investigations into the ice shell in the ocean. We want to know about its composition, its geology. Current activity, we've got tantalizing images from the Hubble telescope that looks like there might be plumes of water vapor coming off of the surface. This isn't so far-fetched. We've seen this at Saturn's moon Enceladus, which is even smaller and colder than Europa is. So this could be happening there. And our last goal is a reconnaissance mission, because eventually we'd like to send a lander there. So to address these 5 goals, we have a gigantic payload on board the Europa Clipper. We have 10 investigations, not 2, not 5, not 7, 10. We have 5 what are called remote sensing instruments. That is, they look at the surface and see what's going on. And we have 5 in situ investigations, which is ones that sense what's around it. We have ultraviolet spectrometers. We have a pair of visible imaging cameras, a narrow and wide angle camera. We have an infrared spectrometer. We have a thermal imager, which is searching for hot spots. We have a radar that can penetrate the ice The radar waves actually go through, and they can image what's at depth and come up the way that our eyes couldn't possibly see. For the in situ instruments, we have a mass spectrometer that will actually absorb chemicals that are coming off of the surface and be able to analyze what they are. We have a dust analyzer that can pick up the larger chunks that the mass spectrometer can't sense. We have a magnetometer, and this is super important because this is how we know there's an ocean there to begin with. It gives off its own magnetic signature. We have Faraday cups, which will measure the plasma that's around it, and that could be complicating the magnetic field. And finally, the most important investigation on here is the one I'm working on, of course, and that is the gravity and radio science investigation, which will tell us about the tidal flexing and how thick the ice shell is. So the Europa Clipper spacecraft is now all assembled, and so this is what it will look like. We've got this magnetometer boom. If you want to measure the magnetic field of Europa, you don't want to measure the magnetic field of the spacecraft, so you stick it way far out from the spacecraft. You've got a high gain antenna to send all your data home. This thing is 10 feet across. That's what it takes to get the signal back from Jupiter. You've got all your instruments that you want pointed forward in the ram direction so that you can sweep up the chemicals. You've got all the remote sensing images pointing downwards. And then you've got the radar antennas, which we didn't have anywhere to put them because you can see the spacecraft is full. So we had to stick them on the solar panels. And that's where they are. They're going to send the signals back, bounce off of the surface and the subsurface, and we're going to see that there. So this is where each of these instruments are on the spacecraft. Just going to step through this. And you'll notice, if I go back there, you'll notice that the most important investigation isn't listed on here. There's no radio science instrument. That's because we don't need one. We just use the antennas that are already on there. You need to send the data home anyway, so you get this investigation for free. So I was talking about the magnetic field. So Jupiter's magnetic field is really intense. And what it does is a magnetic field will induce another magnetic field into anything that's electrically conductive. There's only a few things that could be electrically conductive out here. You either have an iron core or a salty ocean. Right? And we know that Europa's core is just too small to be liquid. It can't be turbulently convecting. It can't sustain its own magnetic field. So that leaves an ocean as the only plausible explanation for why it's got its own magnetic field buried within it. So to do that, to look at this, we're going to send the Europa Clipper into the Jupiter system, and we are not going to orbit Europa. I know that sounds weird, but we have our reasons for that, which I'll get to in a minute. We're instead going to orbit Jupiter, and we're going to do 50 flybys of Europa at different spots so that we get good coverage of the entire thing. If any of you are fans of the original Star Trek series, there's an episode called The Tholian Web. Here it is in real life, but hopefully less deadly. What is not less deadly is the radiation environment. What we have here is a plot of the path the spacecraft will take around Jupiter, and every time it gets close, you'll notice this radiation dosimeter spikes. That is because Jupiter's magnetic field sweeps up all the junk that gets spewed into space by Io and whips it around at really intense speeds, and it crashes into everything. It's a really intense radiation environment. This is not good for our instruments. In fact, it's not good for you. If you were on the spacecraft, you know how long you would survive around Europa? Anyone have a guess? 10 seconds?
Yeah.
20. 2 what? Seconds. 40 minutes. 20. 5 minutes. 2 minutes. All right. Okay. Well, the answer is 0 because there is no air. But if there were, it would be about an hour before you took a lethal dose of radiation. Now, we want to protect our instruments, so all of our electronics are radiation hardened. And in addition to that, they're in a vault of very thick aluminum and titanium to protect it. Even still, you're taking a dose of 300 kilorads inside the vault. So that is why we're not going into orbit around Europa. We're going to orbit at a safe distance and just swing in now and then to take our measurements, just for a few minutes in the danger zone. And then we're going to zip in and zip back out to a safe distance and send all the data back and then do it again a couple weeks later. And that way our mission will last 3 years instead of 3 months. So here's a picture of all of our instruments that are now installed on the spacecraft. And again, you don't get a picture of the antennas because it's not an instrument, it's part of the spacecraft. And so here they are installed on the vault with a person for scale. It was recently shipped to Florida for launch. It got shipped out there in May, and so here's a picture of it being unpacked. And it just completed its final system test yesterday. So it passed that, and we are now in the process of putting the solar panels on it, which are also there. So the panels are here, and this is a picture of them installing the radar antennas on the solar panels. This gives you an idea of just how big this thing is. With the panels installed, the Europa Clipper will be about the size of a basketball court. So here is the size of this spacecraft in comparison to some other things. This is the mythical NASA Space Launch System rocket. This is the Statue of Liberty, not usually found right next to it. This is 6 stacked school buses, and I don't really like this comparison because how often do you see 6 school buses stacked end to end on top of each other? Yeah, right. Here is the Falcon Heavy, which is what we will be launching this on. This is the Europa Clipper. Now you're like, this is not going to fit on there, right? But we can fold all those solar panels up, so it can actually fit in that bulb on the top, the upper stage. And here's a basketball court. We will not be sending a basketball. All right. So our launch date is October 10th, 2024. October 10th is when the launch window opens. We actually have about 4 weeks that we can launch within and still make this trajectory. And it takes about 6 years to get to Jupiter. But that's actually pretty fast, given all the distance that it has to cover. So here it is how we're going to do it. We're actually going to fly by Mars. It's kind of a feeble throw from Earth, and so it just gets past Mars, and Mars causes it to fall back into Earth. And now Earth is going to catch it. Well, it's not really going to catch it, but it'll get a gravity boost from the Earth flyby, and that's what's going to get it out to Jupiter. So there are entire people whose only job is to design these trajectories. That's like jumping off of a moving elevator onto a moving train. Don't do that, but that's what it's like. And it looks like it's going to miss, and yep, it missed. Oh, what a shame. Oh, but that's because Jupiter will catch up to it by the time it falls in, and then they will go about together like that. And then once it's there, of course, it's not going to play on its own. We will not actually be able to see this because all the cameras are on the spacecraft and not off to the side. So that's as good as we're going to get on this. And once we're in the Jupiter system, it will fly by a bunch of the Galilean moons. So we're focusing on Europa, of course, but with the system as complicated as this, we will be doing a few flybys of the others. Now, it's the Europa Clipper, so we're not actually allowed to look at any of the other moons. But we will have to calibrate our instruments. And the best way to do that is to look at these other moons. So it's a sacrifice we're willing to make.
Why are you allowed to look at the other moons?
Because NASA is only paying us to look at Europa. They don't want us to get distracted. Scientists are very easy to distract. So when you get it, this is what it's going to look like after all 49 orbits are on there. From the top down, again, we won't have anything to look at it from the top down. So we also had a campaign over the last couple of years called Message in a Bottle, where you could submit your name to go onto a tiny microchip that will be attached to a tantalum plate in the Europa Clipper vault. We collected over 2 million names from this initiative, beating the same goal set by the Mars Science Lander, because we are the better mission. I mean, it's not a race, but it's a race.
In praise of mystery.
Oh,
A poem for Europa.
I don't know if you can hear this.
Marching under the night sky, inky with black expansiveness, we point to the planets we know. We pin quick wishes on stars. From Earth, we read the sky as if it is an unerring book of the universe, expert and evident. Still, there are mysteries below our sky. The whale song, the songbird singing its call in the bough of a wind-shaken tree. We are creatures of constant awe, curious at beauty, at leaf and blossom, at grief and pleasure, sun and shadow. And it is not darkness that unites us, not the cold distance of space, but the offering of water. Each drop of rain, each rivulet, each pulse, each vein. Oh, second moon, we too are made of water. Of vast and beckoning seas, we too are made of wonders, of great and ordinary loves, of small invisible worlds, of a need to call out through the dark.
So that poem was written for us by U.S. Poet Laureate Ada Limon, and has been engraved on the plate I referred to earlier. This was torture because it was rolled out at all the science team meetings for a year, and we couldn't tell anybody about it because they had to wait for NASA's press release. And so we could only handle this thing with gloves on. And so the poem in Ada Limon's own handwriting is engraved on here. Image of the Drake equation, the message in a bottle, the bottle shown there, and on the reverse side is the waveform of the word water spoken in over 100 languages across the globe. And so here it is being installed in the vault. If you're wondering why it's that odd shape, it's because that's the size of the hole we had left over. There is no extra space on here. All right, you can see everything is, got to find places for cables, you know, to tie this down to. Just cable management on a mission this big is its own task force. So online, we have a whole lot of resources available. Now, there was a live stream from the JPL clean room where this was being built. That has now been taken down because the spacecraft is not there. It is at the payload servicing facility at Kennedy Space Center. And once it's moved out into the vehicle assembly bay, it'll be brought back up there, but right now they can't have anybody in there. So these 10 instruments that I talked about were built at places around the US, and they were all shipped to JPL. At APL, at Johns Hopkins, where I work, we built the radio and the propulsion module and basically the main body of the spacecraft. And then we sent that last year to JPL so that they could put all the instruments into the avionics box and put that on top and do all the environmental testing. And now that's been sent to the Cape. And so we are in the phase called assembly, test, and launch operations. Assembly is done, except for the solar panels that go on next. Testing is done, so now we move on to launch operations. So here are some images, or some places you can go for more information. We have a few more minutes. I think that we do. Are some images from our last Project Science group meeting. We have a partnership with the University of Puerto Rico. So we had our last meeting in San Juan last November. And we invited some students from the University of San Juan in part of our Here to Observe, or H2O program, where they get to shadow team members for the duration of the meeting and then work with them after the fact. This is our deputy project manager, Tim Larson, doing a Spanish language broadcast for our local elementary schools. And nobody on the mission had any idea this guy was fluent in Spanish until he just busted it out in San Juan. And it's like, why are you letting us struggle here when you are like, come on. So there's some presentations by the local astronomy groups and the Planetary Reach program, which is dedicated to bringing astronomy to under-resourced groups. We had an outing at the El Borro Fortress out there. There was a reading of that poem by its Spanish language translator, and we had a bunch of telescopes set up for people to look at. I don't say look through because, as you can see, it's completely overcast here, which is what happens when you plan an astronomy thing. That's just what's going to happen. And there's a lot of press coverage from Puerto Rican programs. And we had outreach activities for middle and high school groups to come through, and we did space activities with them. So we had over 400 students come through that day. And then for undergrad students, we had a Europa Clipper career day with Lori Glaze, who until very recently was the director of planetary science at NASA, but she has just retired. And here is our message from one ocean world to another. This is the Project Science group on the coast of San Juan. And with that, I am happy to take any questions that you might have. Oh, the circles were our Here to Observe partners. Oh, right. 3 months until launch opens. So, all right. Do we have a moderator for questions, or do I just go for it?
Hang on 1 second.
Yep.
Sorry, I was fixing something on the live stream. That's my bad. We lost signal from the presentation. But
no.
It's okay. We got it on the camera, and we're capturing it that way. So, yeah, if you have any questions for Dr. Roberts, I can pass you the mic so that those on the live stream can hear as well. Okay.
Oh,
I think I saw one back here.
While that's going around, I brought stickers. There's a package open back there. If those are gone, they're all up here.
A question I have is the asteroid belt so sparse between Mars and Jupiter that you don't worry about anything going through there?
We get super excited if there's something we can even see with the spacecraft as we're passing through there.
Okay,
Yeah,
so there's
it's always shown in movies and such as this very dangerous minefield that you have to navigate. There's almost nothing there.
wow.
Yeah, it's because if it was like that, they'd crash into each other and take care of the problem pretty quickly. So if you took all the mass in the asteroid belt and crammed it into one giant asteroid, it would still be smaller than the moon.
So how has Mars been pockmarked then? If as the atmosphere left it, smaller planet, it didn't have much atmosphere anyways. How did it become so pockmarked if it wasn't hit by debris?
Oh, it was certainly hit by debris, but not from the asteroid belt.
Oh, okay.
Yeah, but you just get stray meteors coming in all the time, and if you sit there for 4 billion years, that's what's going to happen. But and if you don't resurface yourself the way Europa does, you'll see that forever. So.
All right, do we have another question out in the audience over here?
I just had a question about the gravity assist, because I know this is always used in these, missions. But, the mass of the two bodies stays the same, and of course, as the spacecraft is approaching a planet, it speeds up. But of course, as it's going away from the planet, it's going to be slowed down. So how, if the masses of those two bodies don't change, how do you end up with a net increase in the speed of the aircraft?
That's a great question, because you're right, it doesn't sound like it makes any sense at all. What you're actually getting from the encounter is not velocity, but angular momentum. So what you're doing is you're actually changing the path that it takes, not really increasing the speed so much. And so if I can get my friend to stand up here, all right? All right, go over there by the shuttle. All right? Run this way with your hand out. That's what we're doing. You're just tweaking its velocity, or you're tweaking its direction. Well, you do get an increase in speed out of that, but it's generally it's the angular momentum which is what matters.
My question is, where does that energy come from?
Oh, it comes from the planet itself, but the planet's got so much inertia that it doesn't even notice you taking what you take from it. So when you speed up, you are actually slowing that planet down. But it's also scaled by the mass. The planet has way more mass than any spacecraft we're going to throw at.
The answer is actually an exchange.
It's an exchange, yeah. But it's really more an exchange of angular momentum than it is of mass.
Is the ocean on Europa salty or fresh?
It is salty. We don't know exactly how salty, but we know that it has to be salty because fresh water does not conduct electricity very well. And it has to conduct electricity to generate a magnetic field. But that's one of the questions we want to know is how much salt is there and what kind of salt is it? It might not be table salt or sodium chloride. It could be magnesium sulfate is the other main salt that it could be. And that would have very different implications for what could survive on that. I wouldn't drink it in either case.
So I'm familiar with the concept of a Faraday cage, which is a fully enclosed metallic enclosure. You mentioned that your instrument uses a Faraday cup.
Yes.
So presumably there's an opening. What constraints are there on the size of that opening? Is it behaving like a waveguide beyond cutoff? How are you using it?
Yeah, okay. So I'm getting a little bit out of my depth on this. This is the plasma instrument, and plasma is really just charged particles. So it's collecting, electrons and positive ions, and based on the charge of those, the cup directs it into one one basically counter or another. And so it will sort things by charge. And that's what it will tell us about what the reason we need to know the plasma is because the plasma generates its own magnetic field. And we need to separate that out from Europa's magnetic field, or we'll get confused as to how much salt there is in the ocean.
And up there, we pass this mic down that way.
It's also kind of an inside joke that the instrument is called PIMS, and it's a Faraday cup, if you're familiar with the PIMS cup.
So the main concern is heat because we don't have any heat-resistant material. Since the top layer is ice, could we technically just drill through the planet?
So there have been suggestions of how do we actually get to the ocean, and you're talking about a drill, and yeah, that's one thing that could work. Somebody else has suggested a melt probe, where you basically just get a chunk of plutonium, and it put it inside a ball, and it just sits there and it gives out heat, and it melts its way down through the ice. Of course, if you do that, then you have to figure out how to get any data you collect back out. So you'd have to attach a tether to it or something with like a cable.
And it could melt through the metal too.
Yeah. Although there might be some other problems with sticking a chunk of plutonium there if you're looking for life. They don't like that, right? We have an entire office of planetary protection that tells us how thoroughly we have to clean the spacecraft before we launch. And everything's handled with gloves in a clean room. And yeah.
Doesn't Europa have a lot of radiation?
It does have a lot of radiation. And while that's really bad for any life that would be trying to hang out at the surface, once you get under the surface by even just a few centimeters, few inches, that attenuates all that. It absorbs most of it. So anything that's in the ocean would be totally safe from that.
Yeah, I heard that part. It's just that you said that interfered with the devices on the spacecraft. Wouldn't that make it difficult to land and stay continuously on there?
It
to
would.
manage to dig through the ice?
Right, and that is why we are doing this one first. Because there are a lot of problems we have to solve before we're ready to do a lander. Another one is that if you have ever seen the film 2010, there was a message there that we should absolutely never do that. If you haven't seen 2010, you should go watch it. Or read the book. There's a book.
How long have you been building this spacecraft?
I joined the project in May of 2014. That was before it was officially a project. It was actually greenlit the next year with the payload selection. And
how long have you been working on it before you joined?
Oh, wow. So it's been a long time. Basically since Galileo ended in 2003, people were like, all right, what's next? And they got to work writing and it went through many proposals. There was JIMO, the Jupiter Icy Moons Observer, and then there was the Europa Jupiter System mission, which we were going to partner with Europe, the European Space Agency, and ESA was going to build the Ganymede orbiter, and we were going to build the Europa orbiter, and then we couldn't agree to fund things at the same time, and then neither of them happened, and then Europe just said, you know what, we're going to send our own mission to Ganymede, and then we finally got one to go to Europa. And actually, the European mission launched last year, but it's on a different, less ridiculous rocket, and so it's not moving as fast, so we will actually get there first. But we will be in the same system for a couple of years. And there's one close pass. I mean, we're not at any risk of crashing into each other. That would be super embarrassing. But we'll be able to take, images at the, from two different angles at the same time.
That would be kind of funny if you both planned
Yeah.
like a mission around Jupiter and you both just like crashed into each other.
Yeah.
Why is the launching window in October instead of sooner?
So that's a great question. It's actually super inconvenient for it to be in October because that's like peak hurricane season in Florida. But you have to have the planets in the right position. If I go back, can I go? Oh, this is going to take months to. Almost. There we go. Let's start this over here. We've got to get we don't have enough power in the rocket to go directly there. We need these gravity assists. And so the planets have to be in exactly the right positions for us to get them to go out there. Now, if we could have gotten a SLS rocket, we could have gone straight there, but there weren't any available. Those are being dedicated to the Artemis moon program. So we have to go we're going with the Falcon Heavy, which is got greater availability, and it's also flown a number of times before, so it's very reliable. And if we are somehow unable to make this launch date, and there's no reason to think that we won't make it, but if NASA wants us to go later, we can launch in 2025, we can launch in 2026, but it's always going to be about a year apart when Earth is in the same position relative to Jupiter.
I see.
It's actually funny, if we launch in 2025, we're basically just in a holding pattern for a year until we get onto the 2026 trajectory when Mars is in the right spot, because Mars's orbit is about 2 years. But that at least gets it into space. The most dangerous spot for a spacecraft is on the ground. Once you're in space, you've launched, you're committed. If you're on the ground, anybody can cancel you at the last,
Thank you. Great presentation, by the way.
Thank you.
One question on radar. You mentioned that it's going to penetrate to the ocean. What type of radar are you using?
There are two types of antennas on there. There's HF and VHF. That's high frequency, and
Yep.
I think it's 9 megahertz and 60 megahertz for the two. And so they're for looking at different things. The VHF doesn't penetrate as deeply, but it will get you the surface clutter, and you'll learn a lot more about the surface shape. The high frequency doesn't get you the same level of resolution, but it will go much deeper before the signal is lost. We probably will not be able to see all the way to the ocean, because as the ice gets close to the ocean, it gets warmer and warmer, and that really kills the signal. But you'll know that the ice shell is at least that thick, and you'll know that it's probably not much more than that.
And your studies on, are you using the radar as part of your radio studies as well as
So
gravity?
the radio science is actually done with the spacecraft's data antennas. Usually you would do this with the high gain antenna, the big 10-foot dish. We can't do that on this one because the way this works is you use Doppler tracking to see what happens to the radio signal as you move by the planet. If you go over a particularly heavy patch, you'll speed up, and you'll see that as the signal gets stretched out. If you go over a light patch, you'll slow down, and you'll see the frequency shift the other direction. So if we were to use the high gain antenna, we'd have to point the high gain antenna at Earth. And if you're doing that, you're not then pointing the camera at Europa, and a lot of people would be upset with me. So we are using the fan beam antennas and the low gain antennas, which aren't nearly as powerful, but they spread out over a much larger area. So we can see it in almost any position.
Thank you.
Oh, and that's at X band, which yes.
What date are you supposed to have received all the data?
Well, the prime mission, we get into orbit at 2030. So the prime mission is to end in 2033, I believe. We are hoping, of course, for an extended mission. Whereas if the spacecraft is still functional at the end of it, it's still there, why not keep going? We don't have any requirement to keep going. We can get all our science done with just the 49 flybys that we have planned. But I mean, here's the thing is, we have to do 4 additional flybys whether we want them or not. Because that's what it will take to get us to our end of life. We are going to crash this thing into Ganymede because it must not hit Europa. If there is life on Europa, we don't want to contaminate it with our spacecraft. And Ganymede knows what it did.
But then wouldn't it kill the life on Ganymede?
Ganymede is much less likely to have life. For one, the ice shell is really thick there. So getting anything into the ocean is almost impossible. And the second thing is that there is so much ice on Ganymede that after you go through the ice, then you go through the water, then there's more ice below that. Because the pressure is so great that the ice gets crushed into a different crystal structure and it sinks. So all ice that we know floats on water. But if you squeeze it enough, it'll sink. And so you've got high pressure ice under it. So now you don't have the water touching the rock. And there's no way to get minerals into the ocean. It's just water.
I was just wondering if you could tell us about how this gets deployed. Is there anything complicated about how it gets out of the rocket?
Oh, wow. I don't know the details of that, but there's a long checkout procedure. I mean, so first of all, the solar panels are the first thing that have to deploy. We've got to fold all of these up to get into the spacecraft, into the payload capsule. And that the very first thing is they have to unfurl because that's how we generate all of our power, right? Our battery won't last very long. It's just so we survive launch. And then we need to generate the power. Usually when you go to the outer solar system, you use nuclear power, or it's a radioisotope generator. We don't want to do that here. There's a planetary protection concern, and there also just isn't that much plutonium available. So it was easier for us to go with solar panels. Once that's done, we have to deploy the mag boom. Let me see if I can find a picture of the spacecraft deployed. Here we are. Nope. There it is. This out here. So this is actually, you can't see it in here, but it's a coil. This thing coils up to stow. And you've got these 3 magnetometer sensors out on the boom. So this is, you can't tell from here, it's 25 feet long. That thing is gigantic. And because you don't want to be measuring the magnetic field your own spacecraft is generating. So that's got to stick out. Then you've got to have the covers on all the cameras pop off. Now that's pretty easy because you don't need them to go back on again. So it's just, a frangible bolt, an explosive bolt that just pops the cover off, and then it's it. But you don't want it open during launch because too much can go wrong. There's a cover on the mass spectrometer that has to open up because if you don't open that up, nothing can get in and you have nothing to measure. And then on our way to Mars, we're going to be checking all these instruments out and making sure everything works properly. Basically, you're cooped up in there, waiting for launch, then you actually get to stretch out.
And where does all that happen?
That happens the first year on our way to Mars.
And that's like where it comes out. Where does it come out of the rocket?
Oh, where it comes out of the rocket, that's just as soon as it gets out of Earth's atmosphere.
Okay, and then it's
Yeah.
folded up for part of it.
Right. The rocket is a rocket is basically a gigantic fuel tank, and almost all the fuel is just getting off the Earth, and then you don't need the rocket anymore. It's just dead weight, so you let it go. And in fact, these Falcon Heavies, the boosters normally come back and land, and you can reuse them. Not on this one. We need every ounce of thrust this thing can produce, so we're burning these boosters to their limit. This is the last flight of these. I mean, they have hundreds of them, so it's okay. Yeah, and then it'll come out of the cover because you're out of the atmosphere. You don't care about being aerodynamic. And then all these deployments happen.
Any other questions? We got one more over here. Okay.
So you said like the water absorbs the radiation, like even like a few inches, but wouldn't it eventually mix in with the water later on?
Well, so the radiation is really just tiny charged particles. You're talking about single electrons or protons. There's not that much material. What does the damage is how fast it's moving. And so, yeah, it'll get absorbed by the water. It'll damage that water molecule. But even in just this much water, there are billions of molecules. So.
All right, we do. Oh, you got one? Okay.
Why exactly are you crashing the spacecraft into Ganymede when you're done?
Well, because we don't want it to hit Europa by accident.
Okay.
And this is the easiest thing for us to dispose of it. You can't just leave it in orbit forever because you don't know what it's going to do, especially in a complicated system like this where you've got, I mean, I didn't go into this, but all the moons are pulling on each other. Io, Europa, and Ganymede are in a complicated resonance, tug of war kind of thing. You throw a spacecraft in there, they're going to just knock it around. And you don't know where it's going to go.
Is it going to do anything on Ganymede, or is it just going to, like, crash?
Well, I mean, it would be really nice if we could take pictures on the way in. Did you happen to see the DART experiment last year where we were just taking pictures and pictures of this asteroid as we were going in, and you got that last row right at the top before the signal went dead? Yep.
Incidentally, we do have a talk on DART that we recently just put out, so you can go back on the YouTube channel and check that one out. So I did have a couple of these questions on the chat. We did cover either in this Q&A or during the stream, but we do have one that says, does your team change much over time, or have most of who you've been working on, sorry, that's worded a little weird, or have most of you who have been working on this from the beginning and plan to be there till the end?
So for the science team, that's been pretty constant. We have some people come and go, but most people on the science team want to see this through from the start to finish, because our work really starts when we get the data back. This is just the planning stages. But a lot of the engineers in the technical side will come on for certain phases of the development and then move off onto another project when that phase is over, and be replaced by somebody who's really experienced at the next stage.
Gotcha.
And there are a couple thousand people working on this, so. Yep, I am planning to be at the launch. I'm supposed to find out soon if I get tickets to actually go on base for the launch, but if not, I'm going to be at Playa Linda Beach. So. Coincidentally, we have a science team meeting there that same week. So I have to go to Florida.
All right, any final questions? We got one more here. Okay.
How much did this cost?
Oh. So, it's something like $4 billion at this point.
And we're crashing $4 billion into the moon?
We're crashing well, you know, we don't actually put billions of dollar bills onto the spacecraft. All of that money is spent here on Earth paying our engineers and our scientists to do this development and get us the data back. So we're not going to crash it until we get our money's worth out of it.
All right. So, first off, thank you so much, Dr. Robert. It's amazing. So yeah, we were so happy to have you here, and you mentioned in the in your show about sending your name to Europa. I just want to let everyone know too that happens for other missions as well. So I know they did it for Perseverance when that went. So
we got more names.
Yeah.
It's not a contest.
So yeah, keep that in mind. It's a great way to engage for sure with those missions. With that said, though. It is almost exactly an hour ahead, so that's perfect. So at this point, it's now getting dark enough outside where we can go out and observe. The moon's out, nearly a full moon tonight. So one of the rules at Kopernik is if it's clear skies, you can't leave until you go look through the telescopes. And we have our observatory fully open tonight, 6-inch, 14-inch, 20-inch, and portable telescopes out there. So definitely get a look at all of those. The 20-inch is an imaging scope, so you'll see how that compares to the visual scopes that you look through. So yeah, and also you mentioned the stickers too. Those are there.
I don't want to take these home. We got too many there.
So thanks so much for tuning in. Thank you again, Dr. Roberts, and go out to the scopes.